Time for a lesson on buffers. Now, I know that word sounds kind of weird, but what a buffer is it's a solution that resists changes in pH. And you might be thinking, well, who really cares if I have a solution that resists changes in pH? But what that means is that if you make this solution, this correctly, and you're going to see today how to do that, if you make this buffer solution correctly, you can actually make a solution where if you were to come along and pour some strong acid or some strong base into that solution, it wouldn't change the pH very much. It'll change it just a little bit. So for example, like if I had pure water and I came along and dumped in some 6 molar hydrochloric acid, the pH drops drastically. It goes from 7 to somewhere in the vicinity of 1 pH. If I have a buffer and I take that exact same amount of 6 molar hydrochloric acid and put it in my buffer solution, the pH might go down 0.1 or 0.2 or 0.3. That's all, just a very, very small change. So how is that possible? Well, what's cool is a buffer can also resist changes from adding a base. The same solution, if you pour an acid in, it will resist the change of pH that wants to happen when you add the acid. Or if you add a strong base, it will resist that change. So how is it possible that the same solution could do this? Well, I'm going to show you how it works today, and it actually is directly tied back to our common ion stuff. And the whole idea of common ions is very important in buffers. Before we go any further, I want to tell you why this should be of importance to you. This is actually a life and death kind of situation. I know that sounds really dramatic, but it really is that dramatic. The pH of your blood is around 7.4 or so. Your blood is an example of a buffered solution. Okay, your pH of your blood is 7.4, and it has to stay very tight in that range. If it changes too much, you die. That dramatic. Okay, if you have too much acid or too much base in your solution in your body, your blood in your body was not buffered, you would die if acid or base was added. And I'm not talking about like injecting yourself with hydrochloric acid. Just naturally, our bodies produce all sorts of acids and bases. We consume acids and bases. We're subjected to acids and bases. We inhale things. All sorts of situations could be affecting our blood. But because our blood is a buffer, it has a way of resisting those changes. And that's a good thing for all of us. We'll see some other examples of buffers as time goes on. But what we're going to do first is I've drawn this beaker. Now what I want you to do is get out another piece of paper. You can pause the video if you need to grab one. And I want you to draw a very large beaker in the center of the paper. And this beaker is going to be part of your notes. So you'll keep this with your buffer notes that you're going to be taking for today. Now what we're going to do is figure out how to make this buffered solution. Now a buffer solution is made from either a weak acid and a salt that has its conjugate. So just like we were doing with our common ions, okay, a weak acid and a salt, or a weak base and a salt. Okay, but again, the salt and the weak acid or the weak base, depending on what you have that you're starting with, they have to share an ion in common. Okay, now the example we're going to do with this big beaker here is going to be a weak acid with salt. We're going to use a very common weak acid that we have out there, acetic acid. So HC2H3O2. So if I write the dissociation equation for acetic acid, we know that acetic acid breaks up into H plus and C2H3O2 minus. But notice I used a double-sided arrow because we know that acetic acid only partially dissociates. So what I'm going to do is I'm going to represent in this beaker what this looks like in solution. So if I was to show in this beaker what these ions and molecules look like, we would definitely have H plus. We would definitely have C2H3O2 minuses floating around. But because it's weak, we're also going to have entire molecules of HC2H3O2. Okay. Now also, before we go any further, let's kind of identify how much we have of each one. Now we're not going to actually calculate at this point, but just in terms of thinking about proportionally how much there is, remember this thing was weak. If it's weak, there's not a lot of dissociation that goes on. You saw some problems recently where the percent ionization around 4 or 5 for acetic acid, 4 or 5%. So we can say that once this thing dissociates, that we are only going to have a little H plus. I know that's not a very technical term, and we're only going to have a little acetic acid, okay, but we're going to have a lot of whole molecules floating around in that solution, okay? So that is the acetic acid. Now, to make it a buffer, that's not a buffer. A weak acid by itself is not a buffer. To make it a buffer, we then need to put a salt in. So the salt we're going to put in has to be something that shares a common ion. The one we're going to use is going to be sodium acetate. Okay, sodium acetate. We know it's a salt, starts with a metal, right? So it completely breaks up into Na plus and C2H3O2 minus. Completely breaks up though, right? Salts completely break up. Now, what's going to happen here, if I show this in the beaker, is I'm not going to show any whole molecules, because we said it's going to completely break up. So I'm going to show Na pluses in my beaker, and then I'm going to show C2H3O2 minuses in my beaker. Now, just like before, if we use terms like a lot and a little, this completely broke up. So we're going to have a lot of Na plus, and we're going to have a lot of C2H3O2 minus. So this is what it looks like in the beaker. Now, this was a basic salt that we just added to this weak acid, but bases typically want to react with acids, but they didn't. And the reason why they didn't was because they have a common ion. They both have C2H3O2 minus, so even if they tried to react with each other, nothing would happen. Now, what we have floating around in this beaker now are a bunch of things. Let's look at them. First of all, these ones that we only have a little of, they're not going to really matter in terms of the buffer, okay? The buffer is going to have to do with major components. So anything that there's only a little of, we can kind of disregard, okay? So there's only a little bit of C2H3O2 minus coming from the acid, okay? So this one right here. And then there's only a little of H plus coming from the acid. It's affecting the pH, of course, but in terms of us thinking about how this buffer is going to work, that's not going to be the important part. Also, this Na plus, even though we have a lot of it, it's not going to matter. Remember, in a basic salt, it's the anion that really matters, not the cation. So it's not going to really matter, so I cross it off. If you see what you're left with two things here in your beaker. You've got acetate ion that came from the salt, and you've got acetic acid molecules that came from the acid. And the cool thing about a buffer is that it's a natural system that is both acidic and basic. Right here is the acidic part, and right here is the basic part. And they can coexist in the same container together. Again, that's really cool because normally when we put an acid and a base together, they react and we're done. You know, sodium hydroxide and hydrochloric acid, boom, you make salt and you're finished. Well, here, the acid and base that we have don't interact with each other because they share a common ion. Now, we're not going to get into this until the next lesson. We're just going to leave our buffers as this. So at this point, you should understand how it's made. It has to come from a weak acid and a salt has its conjugate, or a weak base and a salt that has its conjugate. And that you'll end up ultimately with an acidic portion of your buffer and a basic portion of your buffer. Okay, that's where you should be at right now. But in our next lesson, we're going to talk about what happens when we put another strong acid or strong base into this beaker. And if you think about it, let's say we put a strong base in. Which of these two that we circled do you think are boxed in? Which one do you think will attack the base if we put a base in? If you said the acid, yeah, that's what's going to happen. And then if we come along and put a strong acid in, the base part is going to attack it and neutralize it. So we'll get into the neutralization part of it tomorrow. Just for now, you should understand that a buffer resists changes in pH because it has an acidic portion of it and a basic portion of it. Okay, so that's what it looks like. So again, you should have this drawn. You should keep this with your notes because this is going to be really important in our looking tomorrow or in our next lesson at what actually happens when we add something to this solution. Okay, so that's the first part. Now we'll get into some math. Now, the good news is that we're not doing anything different than what we did before. Okay, you see this word buffer in the problem. Well, actually, you see the word buffer, and it doesn't change what we've done. They're asking us here to figure out the pH. They've got a weak acid and then a salt. This is just like the problems you did with common ion. They give you the concentration of both of them. And look, they even gave you already, you didn't even have to dissociate your salt. You know, your salt would go, sodium acetate breaks up into, oops, I don't know why I put that there, breaks up into Na plus and C2H3O2 minus, right? Normally we have to do that, and then we say it's a basic salt, so we're going to use the anion. Well, in this problem, they told it that to us right off the bat. They gave you your acetic acid, they gave you your acetate ion, and then they gave you Ka. So we're going to go ahead and just solve this problem just like you did your other problems for your common ion. So all common ion problems, so problems where you have a weak acid or weak base with a salt, we're going to just write the equation for the weak acid or the weak base. In this case, it's a weak acid. We write that into our table. Put in our initial concentration of our acid here. This will still stay as 0, but instead of having no ion, this time the salt brought some ion. And so this is going to be 0.6. And then the rest of the table is as usual. If you want to pause at this point and do it yourself, and then come and check your work, that's fine. So we end up like that. We know we're trying to find the pH, so this is the box I need, which means I need to figure out what X is. They gave me Ka. You know Ka is C2H3O2 minus times H plus. Sorry, I wrote those flip-flopped, but it doesn't really matter. Like so. Now we know our Ka was given in the problem as 1.8 times 10 to the negative fourth. Remember that negative fourth? We get to take a peek at that and see if we might be able to use our trick. So we're going to have X and then 0.6 plus X, and then over 0.7 minus X. So for our trick, I'm going to get rid of here, and I'm going to get rid of there, and I'm going to solve. So when we solve, we get that X is equal to 2.1 times 10 to the negative fifth. Now, take your calculator while you still have that number in your calculator and divide by the initial concentration of the acid, which was 0.7, times 100 tells us that this thing barely ionized. It's like 0.003%, so we're fine with using our trick. So we're going to come back up here, and we end up here with 2.1 times 10 to the negative fifth. So now I can take that and do what I'm supposed to do in this problem, which is solve for the pH. So the pH equals the negative log of H plus. So my pH is equal to the negative log of, what do we do, 2.1 times 10 to the negative fifth. We want 2 sig figs, so the pH comes out to be, 4.7. All right, now that's what we've done. That's what we've always done. But to be honest with you, because this is a buffer problem, because this is a common ion problem, we actually have a much shorter way to go about doing this problem. Much shorter way to go about doing this problem. And that shorter way has to do with an equation. If you'll flip your paper over, you're going to see what we call the Henderson-Hasselbalch equation. Henderson and Hasselbalch, okay, I won't be silly anymore. Henderson and Hasselbalch, they came up with this equation because the relationship of the acid part of the base part of the buffer is always the same. And because of that, you can really simplify your problems. Let's just take a look at this equation real fast first. So pH is going to be equal to, don't forget that pKa is the same thing as the negative log of Ka. Okay, pKa is the negative log of Ka, and then it'll be plus the log of the base part of the buffer over the acid part of the buffer. Okay, so pH equals pKa plus the log of the base part of the buffer over the acidic part of the buffer. So that same problem we did before, I can do this way. And I think you're going to learn to love common ion / buffer problems, because this equation makes your life way easier. You actually don't even have to make a table. Watch how this works. So we are trying to solve for pH. So we have our Henderson-Hasselbalch equation. So pH is going to be equal to our pKa. So we said the pKa is equal to the negative log of Ka. So pKa is going to be equal to the negative log of Ka, which was 1.8 times 10 to the negative fifth. So that gives me a pKa equal to 4.745. So I can come back over here, 4.745, and it's going to be plus the log. Now, I'm going to do the concentration of the base part of my buffer over the acid part of my buffer. So you have to be able to decide which one's which. Well, we know this is a weak acid. So this is the acid part of my buffer. Therefore, my salt must have been basic, which we already knew that it was. And that is the basic part of my buffer. So I simply put the acid part, which is 0.7, on bottom, the base part on top, like so. And then I plug all of that in my calculator, and I get the pH is equal to 4.7. Flip your paper back over to the front side. It was the exact same problem. Exact same answer. Look at the difference in the work. Which would you prefer to do? I think most of you are saying Henderson-Hasselbalch equation. Now you can do it the table way. I mean, it just takes longer. But the Henderson-Hasselbalch way gives you a much shorter process to go. And it works because that ratio, this ratio we see right here, is what changes the pH. And that's why it's important to have your placement of your substances in the right places for those. But really, it's as simple as that. Okay, cuts down on time drastically. All right, let's take a look at the next example problem. I wanted to show you this one because you want to be thinking about, a different system than that same acid. So this one's a different acid, and this one just tells you your salt. So your acid is lactic acid, which I tell you the formula for right here. And they want us to figure out the pH. As soon as you see this word buffer, you should get a big smile on your face. Because if you see the word buffer, you know you're dealing with a problem that you can use that very short equation for. And so we have our concentration of our acid, we have our concentration of our salt. Okay, this is our salt right here. So the formula is going to be sodium lactate. So Na, and then lactate is C3H5O3. You didn't know that already, but look, you can see it right here in the acid. And then they give you the Ka. So we want to use our Henderson-Hasselbalch equation. So pH equals pKa plus the log of the base over the acid. Okay, pH equals pKa plus the log of the base over the acid. So we're going to be solving for pH. We need pKa. So here's our Ka. Remember, pKa just equals the negative log of Ka. So it'll be the negative log of 1.4 times 10 to the negative fourth. Okay, and if you plug that in, you get a pKa of 3.854. Sorry, 3.854. And then plus the log of the base over the acid. So again, you know this is the acid. It's lactic acid, so it goes on bottom, 0.12. So base is on top, acid's on bottom, so acid's 0.12. And then the salt was a basic salt, and we know that it breaks up in a 1-to-1 ratio. So if this is 0.1, then this is 0.1, and this is 0.1, and this is the part that we care about. So that's your base, so 0.1. And you just plug all of that in your calculator, and you get a pH rounded to 2 sig figs of 3.8. So much shorter than writing out a whole big table, solving for X, going through all of that mumbo jumbo. Just a simpler way. All right, what I want you to do now is I want you to do practice problem number 2. Okay, practice problem number 2. It's a little bit more in depth, a little bit harder of a problem because they're not just having you solve for pH. So I want to point out a few things to you, and I want you to try it, and then tomorrow we'll go over it. Notice they've given you the pH. Okay, they want you to calculate how many moles of NaCl must be added to 2 liters of the 0.1 molar NH3. Notice NH3 is a base. Okay, so when you set up your Henderson-Hasselbalch equation, that base is going to be what's on top. So you're going to have that equation, and at the end, the last part is base over acid. So you're going to be plugging in that 0.1 here. Solve for your acid concentration. Okay, your acid is your salt in this case. It's an acidic salt. Solve for your acid concentration, and then remember that molarity equals moles over liters. If you solve for the acid concentration, you know molarity. They gave you the liters, and you'll be able to solve for moles. And then they gave you Kb. Okay, you're going to have to turn that into pKa. So think about how you might go about doing that. And again, if you have any difficulty, remember we're at the beginning of this. I just want you to attempt this problem. All right.